All right, let's talk about constant acceleration and how we can use that to get the kinematic equations. So by constant acceleration, we just mean that we're increasing at a nice steady rate. So what that would look like on a velocity versus time graph. So if this is velocity and this is time, my graph here would just be a straight line. So maybe it's something like this. It's just some straight line from whatever my t values are. So my initial time, which we're now going to start thinking of as 0, and my some time t here. So I have a nice straight line. I have constant acceleration. My velocity is increasing steadily from time 1 here, 0, up to some other time. So constant acceleration, what does that mean? What can we do with that? All right, well, for starters, if my acceleration is constant, then my instantaneous acceleration at any given point is going to be the same thing as my average acceleration over that time interval. If my acceleration is not changing, then my instantaneous is going to be the same as my average over any interval when my acceleration is not changing. But what is this average acceleration? Average acceleration we defined as delta v over delta t. Okay, so what was delta v? That was our change in velocity. And we had been writing this as v2 minus v1, just to kind of make sure that we knew that this was the first, when we first measured our velocity, and this was the second measurement of velocity. But what you'll see written more often than not in physics books, instead of a 2 and a 1, you'll see the final velocity just written v. And you'll see the initial velocity written v with a subscript of 0. We call that v naught. V naught. So that's going to be how we're going to write our change in velocity. Similarly, with our change in time, we had been writing t2 minus t1. Again, just to get the idea that it's the second time that we measured minus the first time. So the passing of time, whatever that interval was. But we're going to start taking, and again, this is standard, t1 here is going to be 0. We're going to kind of generalize it and say that we start our measurement at 0. And then this t2 right here, we're just going to write that as t. So what does this become? Instead of t2 minus t1, we're just going to write this as t. So the time that has passed. Okay, so now what can we do with this? Well, let's just equate the right-hand side and the left-hand side. We have a string of equals here, so let's just equate this piece and this piece. So what does that give us? Well, that gives us instantaneous acceleration equals v minus v naught, so our final velocity minus our initial velocity divided by t. Okay, now let's solve this for our final velocity. And this will give us our first kinematic equation. So what I'm going to do is I'm going to multiply both sides of my equation by t and t. And so these cancel out, and I'm left with, and I'm going to write it a t on the left-hand side, acceleration times time equals v minus v naught. And then we're going to add v naught to both sides, and so that gives us acceleration times time plus v naught equals v. This right here is our first kinematic equation. It's our first kinematic equation. And in fact, I'll write it the other way around because that's a little more normal. All right, we'll write it v equals v naught plus a t. Just a little bit of rearranging there. So here we have our first kinematic formula. And what this does is this gives us our velocity. We can solve for the final velocity if we know the acceleration, the time that has passed, and our initial velocity. So this is the first kinematic. There's going to be 4 of these. So I'll slide this over here. Okay, so let's look at the second one. Let's look and see if we can find a second kinematic formula. Well, Let's switch colors, we'll do this color. So again, if we have constant acceleration, then this is what our velocity looks like. We end here and we start here. So our velocity goes from our initial velocity here to some velocity up here. And so what's the average of the velocity going to be? Well, the average velocity, if the velocity is increasing steadily, is just going to be the exact middle. So the average velocity is going to be this value right here. So it's going to be dead in the middle between our final velocity and our initial velocity. Well, how do we find the middle? So what we essentially want is the midpoint right here of this interval. Well, we can find that, and we can just write the average velocity this way. This is just going to be the average, literally, of v naught plus v. So v naught and v. And then we take half of that. It's literally the average. We have a constant acceleration. Our velocity is increasing steadily. And so the average is just going to be the mean, the literal average of the initial and the final velocities. Okay, so we have that. But we also said that our average velocity, we also said that in any given case, the average velocity was delta x over delta t. But what was delta x over delta t? And we're going to do the same thing. Instead of x2 minus x1, instead of that, we're just going to denote this as x. And again, because this is what you'll read in most books and you'll see most places, x minus, and instead of our first position, we're going to say naught, x naught. That's going to be our initial. And similarly to above, we're just going to divide this by t, and that's going to denote our change in time because we're assuming that we're starting at 0 time. Okay, so we have these two expressions for average velocity here. Let's set them equal to each other. If they're both average velocity, then they must be equal. So on the left hand, I have v naught plus v divided by 2. It's my average velocity there. And on my right, I have that my average velocity is x minus x naught over t. Okay, up here, we have an expression for our final velocity. Down here, let's try to get an expression for our final position. So I'm going to solve this expression for x, for the final position. To do that, what I'm going to do first is just multiply both sides of this equation by t. So t there, t there. So the t's over here cancel. And on the left-hand side, what I have is t over 2 times v naught plus v. And on the right, I just have x minus x naught. And then if we're just trying to solve for x, then we can just add x naught to both sides. So if we add x naught to both sides, we get t over 2 v naught plus v plus x naught equals x. Okay, so the last thing I want to do, this is our expression right here, but I just kind of want to rewrite it in the more standard form, just rearrange it a little bit. So I'm going to just rewrite it, nothing fancy, but I'm going to switch sides. So x equals, and the way we're going to write this is the initial position plus 1/2 v naught plus v times time. And so this is going to be our second kinematic formula. Our second kinematic formula. So this is number 2. And this is an expression for our final position. And if you kind of think about this, it makes sense. If I want to know where I ended up, if I want to know my final position here, then I can just take my starting position and add to it this quantity. And again, if we remember what this quantity is, this piece right here is my average velocity. That 1/2 v naught plus v is my average velocity. So if I multiply my average velocity by some time t, then that's going to give me a distance. So my final position can be thought of as wherever I started from plus however far I went over some time interval t. So there's our second kinematic equation. In the next video, we'll derive the next two.